The Avogadro constant, denoted as n_a or L, is a fundamental physical constant that defines the number of constituent particles, usually atoms, molecules, or ions, in 1 mole of a substance. Its exact value is 6.02214076 times 10 caret 23 particles per mole 1. This means that 1 mole of any substance contains exactly 6.02214076 times 10 caret 23 of its elementary entities, whether they are atoms, molecules, ions, or other particles. Historical context. The concept is named after the Italian scientist Amedeo Avogadro, 1776–1856, who first proposed that equal volumes of gases, at the same temperature and pressure, contain an equal number of molecules. This hypothesis laid the groundwork for the later development of the Avogadro constant 1. Importance in chemistry. The Avogadro constant is crucial in chemistry for several reasons. Mole concept. It allows chemists to count particles by weighing them. For example, 1 mole of carbon-12 atoms weighs exactly 12 grams and contains 6.02214076 times 10 caret 23 atoms. Stoichiometry. It helps in balancing chemical equations and understanding the proportions of reactants and products in chemical reactions. Molar volume. It relates the volume of gases to the number of moles, which is essential in gas laws and calculations involving gases. Calculation and measurement. The Avogadro constant was historically determined through various experimental methods, including electrolysis, measuring the amount of substance deposited or dissolved at electrodes during electrolysis; X-ray crystallography, determining the number of atoms in a crystal lattice and the volume of the unit cell; Brownian motion, using the movement of particles suspended in a fluid to calculate the number of particles. Modern definition. In 2019, the International System of Units (SI) redefined the mole based on the Avogadro constant. Now, 1 mole is defined as containing exactly 6.02214076 times 10 caret 23 elementary entities. This redefinition ensures that the Avogadro constant has a fixed numerical value, providing greater precision in scientific measurements. 1. Applications. The Avogadro constant is used in various scientific fields. Physics, in calculations involving the number of particles in a given amount of substance. Biology, to quantify the number of molecules in biological samples. Materials science, to determine the number of atoms or molecules in a given volume of material. Example calculation. To illustrate, let's calculate the number of molecules in 18 grams of water, H2O. Molar mass of water. The molar mass of H2O is approximately 18 grams per mole. Number of moles, 18 grams of water is 1 mole. Number of molecules, using the Avogadro constant, 1 mole of water contains 6.02214076 times 10 caret 23 molecules. This example shows how the Avogadro constant bridges the macroscopic and microscopic worlds, allowing us to understand and quantify the number of particles in a given sample. The determination of the Avogadro constant has a rich history involving several ingenious experimental methods. Here are some key historical approaches. 1. Electrolysis. One of the earliest methods involved electrolysis, where scientists measured the amount of substance deposited or dissolved at electrodes during an electrochemical reaction. By knowing the charge of a single electron, Faraday's constant, and the total charge passed through the electrolyte, they could estimate the number of atoms or molecules involved. 2. Brownian motion. Jean-Baptiste Perrin used the phenomenon of Brownian motion to estimate the Avogadro constant. He observed the random movement of particles suspended in a fluid, which was caused by collis ions with the molecules of the fluid. By analyzing these movements, Perrin could calculate the number of molecules in a given volume, leading to an estimate of the Avogadro constant. 1. 3. X-ray crystallography. This method involves determining the number of atoms in a crystal lattice and the volume of the unit cell. By knowing the density of the crystal and the atomic mass, scientists could calculate the Avogadro constant. This approach was particularly refined with advancements in X-ray diffraction techniques. 1. 4. Millikan oil drop experiment. Robert Millikan's oil drop experiment indirectly contributed to the determination of the Avogadro constant. By measuring the charge of individual oil droplets suspended in an electric field, Millikan determined the elementary charge. Combining this with Faraday's constant allowed for a more precise calculation of the Avogadro constant. 1. 5. Modern methods. In recent times, the Avogadro constant has been determined with high precision using methods such as silicon sphere method, counting the number of atoms in a highly pure silicon-28 crystal sphere. This method involves measuring the volume and mass of the sphere and the lattice spacing of silicon atoms. Kibble balance. This method measures the Planck constant and relates it to the Avogadro constant through precise measurements of electrical and mechanical quantities. Redefinition of the mole. In 2019, the International System of Units (SI) redefined the mole based on the Avogadro constant. Now, 1 mole is defined as containing exactly 6.02214076 times 10^23 elementary entities, ensuring that the Avogadro constant has a fixed numerical value 1. These historical and modern methods highlight the ingenuity and precision required to determine such a fundamental constant in science. Molar volume. Molar volume is the volume occupied by 1 mole of a gas at a given temperature and pressure. At standard temperature and pressure, STP, which is defined as 0 degrees Celsius, 273.15 K, and 1 atmosphere of pressure, the molar volume of an ideal gas is approximately 22.414 liters. This means that 1 mole of any ideal gas occupies 22.414 liters under these conditions. Ideal gas law. The behavior of gases can be described by the ideal gas law, which is a combination of several empirical gas laws. The ideal gas law is expressed as PV equals nRT, where P is the pressure of the gas, V is the volume of the gas, N is the number of moles of the gas, R is the universal gas constant, R\approx 8.314 text J/mol times K. T is the temperature of the gas in Kelvin. Empirical gas laws. The ideal gas law is derived from 3 fundamental gas laws. Boyle's law. This law states that the volume of a gas is inversely proportional to its pressure when the temperature and the number of moles are held constant. Mathematically, it is expressed as V proportionality P1 at constant T and N. Charles's law. This law states that the volume of a gas is directly proportional to its temperature when the pressure and the number of moles are held constant. Mathematically, it is expressed as V proportionality T at constant P and N. Avogadro's law. This law states that the volume of a gas is directly proportional to the number of moles of the gas when the pressure and temperature are held constant. Mathematically, it is expressed as V proportionality N at constant T and P. Combining the gas laws. By combining Boyle's, Charles's, and Avogadro's laws, we get the ideal gas law, V proportionality PNT. Introducing the proportionality constant, R, we get the familiar form of the ideal gas law, PV equals nRT. Applications of the ideal gas law. The ideal gas law is used to calculate various properties of gases under different conditions. Here are a few applications. Calculating molar volume. At STP, the ideal gas law can be used to calculate the molar volume of a gas. For 1 mole of gas, N equals 1, at STP, T equals 273.15 text K, and P equals 1 text at D equals PNRT equals the van der Waals equation is a modification of the ideal gas law that accounts for the real behavior of gases, especially under conditions of high pressure and low temperature where deviations from ideal behavior are most pronounced. The equation introduces 2 correction factors, one for the intermolecular forces and another for the finite volume of gas molecules. The van der Waals equation. The van der Waals equation is expressed as P plus Vm2a Vmb equals RT, where P is the pressure of the gas, V_m is the molar volume of the gas, volume per mole, T is the temperature, R is the universal gas constant, A and B are van der Waals constants specific to each gas. Correction factors intermolecular forces. A, the term \frac A, V_m2 corrects for the attractive forces between gas molecules. In an ideal gas, it is assumed that there are no intermolecular forces. However, in real gases, these forces cause the molecules to attract each other, reducing the pressure exerted on the walls of the container. The constant, A, is a measure of the strength of these attractive forces. The larger the value of A, the stronger the intermolecular attractions. Finite volume of gas molecules. B, the term B corrects for the finite volume occupied by the gas molecules themselves. In the ideal gas law, it is assumed that gas molecules have no volume. However, real gas molecules do occupy space, and this volume cannot be ignored, especially at high pressures where the gas molecules are closely packed. The constant B represents the effective volume occupied by 1 mole of gas molecules. The larger the value of B, the larger the volume occupied by the gas molecules. Understanding the correct ion's pressure correction, the term \frac a v_m_2 is added to the pressure P to account for the reduction in pressure due to intermolecular attractions. This correction increases the observed pressure to what it would be if there were no intermolecular forces. Volume correction, the term B, is subtracted from the molar volume V_m to account for the volume occupied by the gas molecules themselves. This correction reduces the available volume for the gas molecules to move around, reflecting the actual free space in the container. Practical implications. The van der Waals equation provides a more accurate description of the behavior of real gases compared to the ideal gas law, especially under conditions where gases deviate significantly from ideal behavior. It is particularly useful for high pressure. At high pressures, gas molecules are forced closer together, making the volume correction B significant. Low temperature. At low temperatures, the kinetic energy of gas molecules decreases, making intermolecular attractions A more pronounced. Example calculation. Let's consider a real gas with known van der Waals constants A and B. By substituting these constants along with the measured pressure, volume, and temperature into the van der Waals equation, we can solve for the corrected pressure or volume, providing a more accurate representation of the gas's behavior. The van der Waals equation is a crucial tool in physical chemistry and thermodynamics, helping scientists and engineers predict and understand the behavior of gases in various conditions. The virial equation provides a more comprehensive approach to describing the behavior of real gases by expressing the pressure of a gas as a power series in terms of its density. This allows for a more accurate representation of gas behavior over a wider range of conditions compared to the van der Waals equation. Let's break down how the virial equation extends beyond the van der Waals correction. The virial equation of state. The virial equation of state is given by RTP equals Vm1 plus Vm2b T plus Vm3c T plus, where P is the pressure, R is the universal gas constant, T is the temperature, V_m is the molar volume, B, T, C, T, etc. are the virial coefficients, which are functions of temperature. Virial coefficients. The virial coefficients, B, T, C, T, etc., provide correct ions to the ideal gas law to account for intermolecular forces and the finite size of gas molecules. Each coefficient represents a different level of interaction. B, T, the second virial coefficient accounts for pairwise interactions between molecules. C, T, the third virial coefficient accounts for three-body interactions. Higher-order coefficients account for more complex interactions involving more molecules. Comparison with the van der Waals equation. The van der Waals equation introduces two specific correct ions, one for intermolecular attractions, parameter A, and one for the finite volume of gas molecules, parameter B. However, it is limited in its ability to accurately describe gas behavior under all conditions, particularly at high densities and low temperatures. The virial equation, on the other hand, provides a more flexible and accurate description by including higher-order terms that account for more complex interactions. This makes it more suitable for describing real gases over a broader range of conditions. Advantages of the virial equation: greater accuracy. By including higher-order terms, the virial equation can more accurately model the behavior of gases, especially at high pressures and low temperatures where deviations from ideal behavior are significant. Temperature dependence. The virial coefficients are functions of temperature, allowing the equation to adapt to changes in temperature more effectively than the van der Waals equation. Systematic improvement. The virial equation can be systematically improved by including more terms, providing a more detailed and accurate description of gas behavior as needed. Practical use. In practice, the virial equation is often truncated after the second or third term for simplicity, as higher-order coefficients can be difficult to determine experimentally. For many applications, the second and third virial coefficients provide sufficient accuracy. Example. To illustrate, let's consider a gas where we use the virial equation truncated after the second term. RTP equals Vm1 plus Vm2b T. This form of the equation can be used to calculate the pressure of the gas given its molar volume and temperature, with the second virial coefficient, B, T, providing a correction for intermolecular interactions. Conclusion. The virial equation extends beyond the van der Waals correction by providing a more detailed and flexible framework for describing the behavior of real gases. It accounts for complex interactions between molecules through higher-order terms, making it a powerful tool in physical chemistry and thermodynamics. Compressibility factor, Z. The compressibility factor, denoted as Z, is a dimensionless quantity that measures how much a real gas deviates from ideal gas behavior. It is defined as Z equals RTPVM. where P is the pressure, V_m is the molar volume, volume per mole, R is the universal gas constant, T is the temperature. For an ideal gas, Z is exactly 1 under all conditions. However, for real gases, Z can differ from 1, indicating deviations from ideal behavior. Significance of the compressibility factor. The compressibility factor is significant because it provides insight into the extent and nature of deviations from ideal gas behavior. Here's why it's important: deviation from ideal behavior. By comparing the compressibility factor to 1, we can determine whether a gas behaves more ideally or deviates significantly. If Z is close to 1, the gas behaves almost ideally. If Z is much greater or less than 1, the gas exhibits significant non-ideal behavior. Intermolecular forces. The value of Z can indicate the presence and type of intermolecular forces. For example, Z1 indicates attractive forces dominate, causing the gas to compress more than an ideal gas. Z1 indicates repulsive forces dominate, causing the gas to occupy more volume than an ideal gas. Critical point and phase transitions. The compressibility factor helps in understanding the behavior of gases near their critical points and during phase transitions. Near the critical point, gases show significant deviations from ideal behavior, and Z can vary widely. Generalized compressibility charts. To simplify the use of the compressibility factor, generalized compressibility charts are often used. These charts plot Z as a function of reduced pressure P_r and reduced temperature T_r, where PR equals Pcpan TR equals TCT. Here, P_c and T_c are the critical pressure and critical temperature of the gas, respectively. These charts allow for the estimation of Z for different gases under various conditions without needing to perform complex calculations. Practical applications. The compressibility factor is used in various practical applications, including chemical engineering, designing equipment and processes that involve gases, such as reactors, compressors, and pipelines. Thermodynamics, calculating thermodynamic properties of gases, such as enthalpy, entropy, and internal energy. Petroleum industry, estimating the behavior of natural gas and other hydrocarbons under reservoir conditions. Example calculation. Let's consider an example where we need to calculate the compressibility factor for a gas at a given condition. Suppose we have a gas at 10 at pressure and 300 K temperature, with a molar volume of 2.5 liters per mole. Using the ideal gas law, we first calculate the expected volume. Virial equals PRT equals definition of fugacity. Fugacity can be thought of as an effective pressure that accounts for deviations from ideal gas behavior. It is a corrected pressure that makes the behavior of a real gas resemble that of an ideal gas under the same conditions. Mathematically, fugacity, F, is related to the pressure P of a gas through the fugacity coefficient, \phi. F equals P. Fugacity coefficient. The fugacity coefficient, \phi, is a dimensionless number that quantifies the deviation of a real gas from ideal behavior. For an ideal gas, \phi is equal to 1, meaning the fugacity equals the pressure. For real gases, \phi can be greater or less than 1, indicating non-ideal behavior. \phi 1 the gas exhibits attractive intermolecular forces. \phi 1 the gas exhibits repulsive intermolecular forces. Role of fugacity in non-ideal gas behavior. Fugacity plays a crucial role in understanding and predicting the behavior of real gases. Here are some key points. Thermodynamic equilibrium. Fugacity is used to determine the equilibrium state of a system. For a gas in equilibrium, the fugacity of the gas phase must equal the fugacity of the liquid phase. This is essential in phase equilibrium calculations. Chemical potential. Fugacity is directly related to the chemical potential \mu of a substance. The chemical potential is a measure of the potential energy of a substance to undergo a phase change or a chemical reaction. For a real gas, the chemical potential is given by mu equals plus RTLN FF, where \mu circ is the standard chemical potential, R is the gas constant, and F \circ is the standard fugacity. Phase equilibria. Fugacity is crucial in phase equilibria calculations. For example, in a mixture of gases, the fugacity of each component must be equal in all phases at equilibrium. This helps in determining the composition of each phase. Non-ideal solutions. In solutions, fugacity is used to describe the behavior of components. The fugacity of a component in a mixture can be related to its concentration or mole fraction, allowing for more accurate predictions of behavior in non-ideal solutions. Practical applications. Fugacity is used in various fields, including chemical engineering, designing processes involving gases and liquids, such as distillation, extraction, and absorption. Petroleum industry, predicting the behavior of hydrocarbons in reservoirs and during processing. Environmental science, modeling the behavior of pollutants in the atmosphere. Example calculation. To illustrate, let's consider a real gas at a given pressure and temperature. Suppose we have a gas with a pressure of 10 atm and a fugacity coefficient of 0.95. The fugacity can be calculated as F equals P equals 0.9510 atm equals 9.5 atm. This means that the effective pressure of the gas, accounting for non-ideal behavior, is 9.5 atm. Conclusion. Fugacity is a powerful concept that extends the ideal gas law to real gases, providing a more accurate description of their behavior. It is essential for understanding phase equilibria, chemical potential, and the behavior of non-ideal solutions. Fundamental to the mole concept. Avogadro's constant, N_A, is central to the definition of the mole, which is a fundamental unit in chemistry. 1 mole of any substance contains exactly 6.02214076 × 11 entities, atoms, molecules, ions, etc. This allows chemists to count particles by weighing them, making it possible to relate macroscopic measurements to microscopic quantities. 2. Stoichiometry and chemical reactions. In stoichiometry, Avogadro's constant is essential for balancing chemical equations and determining the proportions of reactants and products. It allows chemists to convert between the mass of a substance and the number of particles, facilitating the calculation of reactant and product quantities in chemical reactions. 3. Determining molar volume. At standard temperature and pressure, STP, 1 mole of an ideal gas occupies 22.414 liters. This relationship, derived using Avogadro's constant, is crucial for understanding gas behavior and applying the ideal gas law PV equals nRT. It helps in calculating the volume of gases involved in reactions and processes. 4. Relating macroscopic and microscopic properties. Avogadro's constant bridges the gap between macroscopic measurements, such as mass and volume, and microscopic properties, such as the number of atoms or molecules. This connection is vital for understanding the physical and chemical properties of substances at the atomic and molecular levels. 5. A basis for modern definitions of units. The redefinition of the mole in 2019, based on Avogadro's constant, ensures greater precision in scientific measurements. By fixing the value of N_A at 6.02214076 × 10⁻23, the mole is now defined as containing exactly this number of entities, providing a stable and precise foundation for measurements in chemistry and physics. 6. Applications in physics. In physics, Avogadro's constant is used to calculate the number of particles in a given amount of substance, which is essential for understanding phenomena at the atomic and molecular scales. It is also used in statistical mechanics and thermodynamics to relate macroscopic properties to microscopic behavior. 7. Biological and medical applications. In biology and medicine, Avogadro's constant helps quantify the number of molecules in biological samples. This is important for understanding biochemical processes, drug interactions, and the behavior of biological systems at the molecular level. 8. Material science and nanotechnology. In material science, Avogadro's constant is used to determine the number of atoms or molecules in a given volume of material. This is crucial for characterizing materials, understanding their properties, and designing new materials with specific characteristics. In nanotechnology, it helps in quantifying and manipulating materials at the nanoscale. 9. Environmental science. Avogadro's constant is used in environmental science to quantify the concentration of pollutants and other substances in the atmosphere, water, and soil. This is important for monitoring and controlling environmental pollution and understanding its impact on ecosystems and human health. 10. Educational importance. Avogadro's constant is a fundamental concept taught in chemistry and physics education. It helps students understand the relationship between macroscopic and microscopic properties, the mole concept, and the principles of stoichiometry and gas laws. It is a cornerstone of chemical education and essential for developing a deep understanding of chemical and physical principles. Example calculation. To illustrate the practical use of Avogadro's constant, let's calculate the number of molecules in 18 grams of water, H2O. Molar mass of water. The molar mass of H2O is approximately 18 grams per mole. Number of moles, 18 grams of water is 1 mole. Number of molecules using Avogadro's constant. 1 mole of water contains 6.02214076 times 10 carat 23 molecules. This example shows how Avogadro's constant allows us to relate the mass of a substance to the number of molecules, providing a clear understanding of the quantity of matter at the molecular level. Conclusion: Avogadro's constant is a fundamental constant in science that plays a crucial role in various fields, from chemistry and physics to biology and environmental science. It provides a bridge between the macroscopic and microscopic worlds, enabling precise measurements and a deeper understanding of the behavior of matter. That was all. Goodbye.